So our next speaker is Michael Wakin, who's going to be speaking about an efficient dictionary for reconstruction of sampled multiband signals.
Okay, thank you very much. This is joint work with Mark Davenport, and we hope to have a preprint available very soon with a lot more detail on all of this work. So please feel free to contact either of us for more information. So in the 1960s and 70s, David Slepian wrote a beautiful series of papers studying the effects of time and band limiting operations on analog and digital signals. Much of this work is not that widely used and perhaps not that widely known these days when people are focused more on things like sparsity. But this talk is about how we can apply some of David Slepian's original ideas in developing a basis that gives us efficient sparse representations for many signals of interest. In particular, one of the applications of a sparse representation is, of course, in something like compressive sensing. And as many people are familiar with here in the audience, a typical compressive sensing setup looks something like this, where you have a discrete finite vector x. You hit it with a compressive matrix multiplication, and then you try to recover x from y using some type of sparse dictionary or model for the structure of x. Now, obviously, one of the kind of killer applications of compressive sensing could be if we could use these kinds of ideas to simplify the way that we sample and acquire very high bandwidth analog signals that maybe obey some type of sparse model. And inspired by that type of thinking, there have been various randomized measurement hardware devices that have been proposed and built over the last several years, and various types of kind of customized reconstruction techniques that are developed appropriately to exploit the structure in X. Much of this work, however, either operates outside the standard matrix vector multiplication framework that's so sort of classical in compressive sensing, maybe familiar to a lot of us, and also very well studied in terms of, say, algorithms. Or this work involving analog signals, when it does involve this matrix vector multiplication framework somehow, doesn't necessarily, as we'll see today, doesn't necessarily use the most efficient basis or dictionary for reconstructing X. So we'll kind of touch not only on the theme of sparse representation here today, but kind of reconciling the analog and digital compressive sensing frameworks in an efficient way. Our approach to reconciling these frameworks is really based on two considerations. One is a way that we could think about mapping the analog sensing process into something related to, or something that looks like, matrix vector multiplication. And two is how can we kind of map whatever sparse or structured model we have for our analog signal into an efficient sparse basis for a digital vector. The first of these topics I will mention only on one slide, actually. I would just like to kind of say the following in order to justify the second of these points, which will really be the focus of the talk. So any type of linear measurement you take of an analog signal can be written like this. It can be written as an inner product between your analog signal x of t and some sensing functional phi of t, assuming only that x is band limited, maybe with some very, very high bandwidth. Then you can write x as a weighted sum of sinc functions, where the weights are given by the Nyquist rate samples of x of t. But just graphically envisioning what this equation means, it means that you could view a discrete streaming set of measurements, at least implicitly, as an infinitely large matrix times a streaming set of Nyquist rate samples of x of t. Now, what matrix goes here depends on what type of measurement you're taking, what type of hardware you're using, and so on. But certainly there exist measurement schemes that have been proposed to date in which it would be fair to say if you take a finite window of measurements, call that a vector y, you could write those as a truncated finite matrix, call that phi, times a truncated set of Nyquist rate samples of x of t. Depending on your sensing architecture, this may be approximate, this may only be an approximation to y, or in some cases this could literally be an exact representation for y. So having said that, the real focus of this talk is coming up with good sort of discrete domain sparse representations for vectors x that have this form. So our objects of interest are really length n vectors consisting of Nyquist rate samples of some original analog signal. Of course, if we have such a sparse representation, then we can use that to recover x from y under this kind of modeling, under this kind of measurement framework. So again, this is our object of interest. We call it X. It's a length n vector of Nyquist rate samples. And we'd like to find a good digital domain dictionary. We'll call that psi, and characterize the sparsity level of the coefficient vector for X within that dictionary. Okay, so of course the appropriate type of dictionary to use here will depend on what type of structure do we want to assume for our analog signal kind of at the front end. And there's a couple of options that are worth mentioning here. One is that we could just assume like a so-called multi-tone model, where your analog signal, you just assume it can be written as a sum of S sinusoids whose frequencies are unknown, but they are known to be restricted to a discrete grid of possibilities in the analog spectrum. This is the so-called Nyquist grid. If your analog signal obeys that assumption, and you take just n Nyquist rate samples of that signal, and you analyze those in the DFT dictionary, then you get a coefficient vector which is exactly S sparse. So this is a very elegant way, right, that an analog concept of sparsity can map into a digital concept of sparsity. However, this model is somewhat restrictive or arguably artificial, especially the assumption that the tones would live exactly and precisely on this harmonic grid. So a somewhat more flexible model that's been considered in the literature is what's known as a multiband model. This will be what we assume for today's talk. In the multiband model, we assume that the overall Nyquist bandwidth of our signal, which again we think of as being very, very wide, we imagine that being partitioned into blocks, and we suppose that k of these blocks in the analog spectrum can be non-zero, but that the remaining blocks in the analog spectrum will be zero. The positions of the k known block, the positions of the k active blocks are unknown, except just for kind of simplicity, we do lock them onto this grid here. You don't actually lose that much generality by doing this. And these spectra within the active blocks can be arbitrary. So I've just drawn them as being flat here, but that's just keep the drawings clean. It's not really a necessary assumption. So actually, over the past several decades, there has been work that has considered this analog signal model, and actually some very nice theory developed for fundamental sampling bounds on these types of signals, specialized sampling protocols to capture the information in these signals, and specialized techniques for reconstructing these signals from samples. I would claim, though, that that work is of independent interest from today's talk because we are specifically focusing on the problem where we have a length n vector of Nyquist rate samples of our analog signal that comes from this model, and we want to come up with a good sparsifying discrete domain dictionary for that length n sample vector. So to explain why this problem is challenging, but also kind of give a flavor of the solution, let me consider a little bit simpler signal model, just temporarily here, where within the very wide analog bandwidth of our signal, we suppose that just one low-pass band is occupied. It's got width B and it's centered at DC. Once we come up with a good dictionary for sample vectors coming from this signal model, then we will extend that dictionary back to the multiband case here in a few minutes. Okay, so imagine an analog signal with a spectrum like the one shown here. And imagine that you sample this, and you take the infinite stream of samples from minus infinity to infinity. So now you do frequency analysis on this. You look at the DTFT, discrete time Fourier transform. The spectral replication theorem says that if you sample this at the, well, in particular at the rate B Nyquist, which we're considering to be the Nyquist sample rate, if you sample at the Nyquist rate, then the DTFT is a copy of the continuous time Fourier transform, and the frequency axis is remapped so that the width of this band is now 2 times W. It goes from minus W to W in particular, where W is given by the ratio of B to B Nyquist. Okay, so here the sparse structure, this nice clean sparse structure of the analog spectrum is passed on to a sparse structure in the discrete time spectrum. So let's hang on to this, and I'm moving this to the top of the slide now. This is our discrete time, infinitely long stream of samples. The problem, of course, comes when you time limit these samples, and you get our sample vector x, which has length n. The conventional way of doing frequency analysis of a vector is to use the DFT, which says we try to build up X as a weighted sum of sinusoids whose frequencies are chosen from a finite discrete grid. For this slide and for future slides, EF here denotes a length n vector. It is a set of samples of a complex exponential pure tone with digital frequency f. So the DFT says we're building up X as this weighted sum of these sampled complex exponentials with discrete frequencies. And of course, as you know, anyone who's had experience with signal processing and windowing knows, I mean, windowing in time is convolution and frequency, and so this nice structure in our spectrum gets smeared out in the DFT domain, and we no longer have something which is sparse. There are some tricks you can play. You can apply smoother windows in time to try to improve the decay of these side lobes in frequency, but you don't still approach anything that's sort of nearly as sparse as you might like or hope to achieve, given kind of structured model that your original signal obeys. It might not at this point be clear that there's much else that can be done, but we can arrive at a different sort of solution by taking an alternative perspective on this problem. So let's go back to our infinite stream of samples and look what happens when we time limit this set of samples to just have length n. Well, you can bring that time limiting operation inside the DTFT synthesis integral. And this says that our sample vector x, I'm just going to rewrite this on the next slide here. So this is exactly the same equation. Our sample vector x can actually be written not just as a discrete sum of complex exponentials, but as an integral of complex exponentials that are time limited, just like x, with frequencies between minus w and w. So I like to view things geometrically. Here's kind of a conceptual rendering of what's going on here. These EF vectors, they live in Cn, they're n-dimensional. And as the frequency varies from minus w to w, they trace out this one-dimensional manifold within this space. And this synthesis integral is saying that if we just take tiny little pieces of this manifold and weight them all maybe differently and add them all up, then we can build up our sample vector x. So this sounds kind of like a basis. Of course, the problem is that there are infinitely many signals on this manifold, and we're only in a finite dimensional space, so we haven't exactly solved the problem here yet. But wouldn't it be great if there was some structure to this manifold? Like, for example, if it lived within a low-dimensional linear subspace, then all we would need is a basis for that subspace, and we would have a good basis for representing x. Unfortunately, this manifold will not live within a low-dimensional linear subspace. Its span is collectively actually n-dimensional. However, it actually does live very, very close, quantifiably close, to a very low-dimensional subspace of Cn. And we can see that in the following way. So let's suppose that over all k-dimensional subspaces of Cn, we want to find the best subspace Q that approximates the manifold in a least squares sense. So we want to minimize the average projection error between a sampled complex exponential and the projection of that vector onto the subspace Q. Well, actually, when you work through the equations involved in solving this problem, you end up looking for the eigendecomposition of a particular type of matrix. And that matrix appears in one of David Slepian's papers, and it's known that the optimal solution that would solve this problem on this slide is given by the first k, what are called DPSS vectors. So Slepian proposed these discrete prolate spheroidal sequences as follows. You give an integer n and a digital frequency cutoff w. The DPSSs are a collection of n vectors. They each have length n. And each one satisfies an eigenequation like this. You take any one of them, you take that vector, you zero pad it, and then you take its DTFT, and you band limit that, you sort of low-pass filter that signal to have frequency cutoff W. Then you go back to the time domain, and you restrict that signal in the time domain, once again to have length n. You get back exactly the same vector that you started with, but scaled by some eigenvalue, lambda L, which is between 0 and 1, always. So these things are eigenvectors of the process that first band limits and then time limits a signal. By definition, these things are perfectly time limited, but when the eigenvalues are close to 1, as we will see, this can happen, These signals are also very, very highly concentrated in frequency. So nothing can be both band limited and time limited. These, subject to the constraint of being time limited, are as maximally band limited as possible, in fact. The eigenvalues are of great significance when talking about these DPSS vectors, and this is a plot of the behavior of the eigenvalues for an example pairing when n is 1024 and w, the digital frequency cutoff, is 1/4. The eigenvalues are sorted from large to small. They tend to cluster very close to 1. There's a very sharp cutoff, and then they tend to cluster very close to 0. This is a log scale here, and these are about 15 orders of magnitude smaller than the ones at the top. Moreover, this cutoff tends to happen around 2 times n times w, which in this example is 512. So as a rule of thumb, the first about 2 and w eigenvalues are very close to 1. The remaining eigenvalues are very close to 0. Here's a plot of some of these vectors in the time and frequency domains. They are, again, perfectly time limited, and they are approximately band limited between the frequencies minus w and w. So going back to our manifold approximation problem, the optimal subspace for approximating our manifold is spanned by the first k DPSS vectors, and analytically, we also know how good this approximation is. The mean square error you make in projecting the manifold onto this subspace is given by the sum of the eigenvalues that you leave out after you've taken the first k basis functions. And so if you choose k to be around 2 times n times w, then you'll be adding up a bunch of numbers that are very close to 0, and you will get that the manifold must live very close to that 2nw dimensional subspace. We can check that on a frequency by frequency basis. This is a plot showing, as a function of the digital bandwidth f, what's the SNR we get when we take any one of these sampled complex exponentials and project it onto the manifold. When we choose k to be about 2nw or a little bit smaller, we actually get about 20 to 30 dB worth of approximation, worth of SNR for most sinusoids between minus w and w, but we lose a little bit at the tails here. However, if we go a little bit larger than 2nw, we actually get extremely high quality approximation of all of these sampled complex exponentials, about 2 to 300 dB of SNR here in this kind of MATLAB experiment. So this is just talking about approximating sampled complex exponentials, but again, those are building blocks for the sample vectors we would get by sampling low-pass signals. And so we make this more precise in our paper, but the message is that most band-limited analog signals, when you sample them and time limit them, will be very well approximated by the first k DPSS vectors, if we choose k to be on the order of 2 times n times w. Now the reason this says most here and not all is a little bit subtle. It's more than I would have time to go through in this talk. We do make this more formal in our paper. You can interpret most like in a probabilistic sense, for example. But there are exceptions, and we will do our best to kind of argue as well that those exceptions really are kind of pathological. Now that we've talked about building up sample vectors from low-pass signals, we can extend this to the idea of building up sample vectors from band-pass signals. It's a very simple translation. You just take your baseband DPSS vectors and you modulate them up. You multiply them by sinusoids to move them up to any other center frequency that you like. And this now brings us to our construction of the multiband DPSS dictionary. If we're going to have some signals with an unknown multiband spectrum, then we can build up a dictionary for these types of signals by taking our k DPSS baseband functions that we were just talking about, modulating them up to the center frequencies of every one of the candidate bands that could be occupied by our signal, and then just concatenating all of these smaller dictionaries together into one larger dictionary. This is a matrix with n rows, and it has approximately n columns. And the takeaway message here is that most multiband analog signals, when you sample them and time limit them, will be very well approximated by a sparse representation in this dictionary. So the key word here is now sparse. In particular, if you have an example like this where the 2nd, 4th, and 8th bands are the ones that are occupied, then you only really need the second, fourth, and eighth parts of this dictionary to build up the sample vector coming from that analog signal. So we can study the interactions of this dictionary with compressive measurement matrices. In particular, if you build a measurement matrix phi with m rows, where m is on the order of s log n, then with high probability the product of phi and psi will satisfy the RIP of order s. And so translating this into our multiband model, if we have k occupied bands, each with analog bandwidth b, this is the sparsity level we would anticipate in our dictionary. And so if you look at the overall number of measurements you need, number of random measurements you would need to reconstruct this sparse vector, that would scale, aside from a log factor, that would scale like k times b over b Nyquist. And relative to the overall Nyquist bandwidth, this is the amount of occupied analog bandwidth. So this really is the analog information level, or the so-called Landau sampling rate for this signal. And again, while there are other schemes of achieving or approaching the Landau sampling rate, this is one that is, specifically formulated in this setting where we have just a discrete length n truncated set of Nyquist samples. There's more that can be said. In particular, we could try to exploit the block sparse structure of our coefficient vectors that we anticipate. Going back to my last example, we would expect actually only alpha 2, alpha 4, and alpha 8 to be non-zero. The rest could be 0, for example. And that structure can allow you to reduce the number of measurements you need. You can just prove like a block RIP that takes fewer measurements. You can improve upon the log factor on the previous slide. And then you can use recovery techniques that are adapted to that block sparse structure. We use one of these, we use the block cosamp technique in the example on this slide. So here we simulate an analog signal where each occupied analog band has a width 1 over 512 times the overall Nyquist bandwidth. We have 5 occupied bands. We take 1,024 Nyquist rate samples. That's our vector x. This vector in our dictionary, in our multiband DPSS dictionary, has a sparsity level of about 45. This is the spectrum of that time-limited set of samples that we acquire. We take 128 random measurements of this length 1024 sample vector, and then we try to recover it. And first we recover it using block cosamp in our multiband DPSS dictionary. And the recovery is quite accurate. We have 54 dB of SNR in our recovered signal. In contrast, the DFT as a recovery dictionary here would struggle quite a bit because we don't have these nice pure tones that are locked onto a discrete grid. Here's what we recover using the DFT basis as a sparsifying dictionary. We do recover the dominant frequencies, but we miss these actually important side lobes away from the dominant frequencies. We're much worse in terms of SNR, and shown right here, we actually recover a sort of proclaimed dominant frequency, which is actually not a dominant frequency in our original signal. Very quickly, there's other things you could think about aside from doing signal recovery with this idea that these sample vectors can live in low-dimensional subspaces. For example, imagine that some portion of your analog bandwidth was going to be occupied by some interfering signal. You knew where it was going to be. You knew you didn't want it, but it's going to be there, and you would like to kind of remove its influence from the measurements that you've taken. Well, this is possible to do now that we know the sample vectors just from that interferer alone will live in a low-dimensional subspace. You don't have to know what the interferer is exactly. You can construct an orthogonal projection operator to remove the influence of that interferer from your measurements. After that, you could solve whatever type of problem you like for your signal that remains. You could solve a recovery problem, or you could do things like detection or estimation that don't even require ever doing any type of signal recovery. So to wrap things up, we've talked here about a new type of multiband modulated DPSS dictionary that can efficiently represent most sampled multiband signals with sparsity levels much better than what you would achieve using the standard DFT. Our paper will have a lot more details about this work. In particular, there is a little bit of a challenge in appropriately setting this parameter k, the dimension of your subspace. You want it to be large enough that you get good approximation performance for most signals, but you want it to be small enough that you don't disrupt the coherence properties of this dictionary that you get when you start concatenating all these things together. The good news is there does appear to be a sweet spot, though. And also, it's worth mentioning other related work that's appeared in the last couple of years that also kind of builds on at least one of the themes that you saw in today's talk. These papers are quite interesting, although we do consider kind of a different type of problem. To the best of our knowledge, none of these works or any other to date have specifically considered quantifiable approximation bounds, specifically for sampled multiband signals, and also applied these bounds for developing theory and sort of reconstruction techniques for compressive sensing and RIP type of results. So again, please contact us if you'd like any more information, and I'll be happy to take any questions you might have. So thanks very much. Thank you. Thanks again for the invitation.
Yeah, this is very interesting.
It's been a pleasure to be here.